Ladies and gentlemen, if you could take your seats, please. Good evening. On behalf of the British Geotechnical Association, I'd like to welcome you to the Great Hall here at Imperial College. My name is David Toll. I'm chair of the BGA, and I'll be your chair for this evening's event. So before we start, we have some housekeeping announcements. I would ask everybody to switch their mobile phones and electronic devices to silent mode. So I see a few hands going into pockets. Thank you. No fire alarm tests are planned for this evening, so if you hear an alarm, it will be real. In the event of a fire, we need to proceed calmly and promptly out of the theatre, where further instructions will be given. And the emergency exits are to be found on either side of the lecture theatre. And so, now to the lecture. My Lord, ladies and gentlemen, distinguished guests, it is a great honour and a privilege to welcome you to Imperial College for the 61st Rankine Lecture. As usual, tonight's lecture is being webcast live to an international audience, and I welcome our online audience. And also, we have an overflow lecture theatre here at Imperial College. A very good evening to you all here in presence and online. So this 61st Rankine Lecture will be delivered by Professor John Carter, Emeritus Professor, former Pro Vice-Chancellor, Dean of Engineering at the University of Newcastle, New South Wales, Australia. Over the years, I've met with John in many parts of the world, including in his home at Newcastle, Australia. So it's a particular pleasure this evening to welcome him here to London. The title of his lecture is Constitutive Modelling in Computational Geomechanics. Maybe not a surprise for those of you who know John. And to introduce the lecturer, I call on Professor Mark Randolph of the University of Western Australia to give an introduction.
Good evening, everyone, both those here in the hall and those watching online. It gives me tremendous pleasure to have the honour of introducing Professor John Carter, tonight's Rankine lecturer for the British Geotechnical Association. John and I first met and collaborated at Cambridge in the late 1970s, and we've continued as close friends and colleagues since that time. I had already decided to make the journey here from Australia to listen to tonight's lecture, breaking a drought for me of 3 years, but was then delighted when John invited me to give the introduction. John was raised in Sydney, going through the state school system at Unwary Boys High School. He's the youngest of 3 children with 2 elder sisters, in fact, women always tending to outnumber the men in John's close family. His parents both had connections to the written word, his father a bookbinder and his mother working in the printing industry. John was the first of his family to attend university, obtaining his bachelor's degree in civil engineering from the University of Sydney in 1972 through a cadetship with the then Electricity Commission of New South Wales. As a young graduate engineer, he worked on the design and construction of coal-fired power stations and admits to now feeling his age as they start to be decommissioned, not before time. Continuing at the University of Sydney, he undertook a PhD on large deformation analysis of elastoplastic soils, an area that has remained of particular interest and in which he has made several seminal contributions. His supervisor was Professor Ted Davis, but he also worked closely with Dr., later Professor John Booker. I suspect that John's skills in university politics, which he applied with great success in the later stages of his academic career, have their roots in John Booker's mentorship. During his PhD, John spent a year at King's College working with Professor Bob Gibson. Then, at the end of his PhD, he returned to the UK to work with Professor Peter Roth, then at Cambridge University, on effective stress approaches to modelling the successive stages of installation, consolidation, and loading of driven piles. The outcome from that project has continued to form the basis of our current understanding of the various processes involved. It would come as no surprise to anyone meeting John that he had been a competitive rugby player, both while growing up in Sydney and in Cambridge. John is very much a family man, marrying his wife Heather during his PhD and raising 2 daughters between them. To date, they have 4 children, the last of whom, breaking the trend, is a grandson. They're fortunate to have both daughters and their families now living locally, close to them in Newcastle. John has held academic positions at the Universities of Queensland, Sydney, and finally Newcastle, till retiring as Emeritus Professor in 2013. He also spent a sabbatical year at Cornell University in 1986, working with Professor Fred Kulhawi, producing together the widely used design manual on analysis and design of drilled shafts for the Electric Power Research Institute. At the University of Sydney, John rose to be Challis Professor in Civil Engineering and undertaking a number of administrative roles, including Chair of the Research Committee and also of the Academic Board. These roles paved the way for his appointment in 2006 as Pro-Vice-Chancellor and Dean of Engineering at Newcastle. The main scientific thrust of John's career has been in computational geomechanics, developing his own finite element code, Athena, during his PhD, at a time when there were few, if any, comparable tools. He's been at the forefront of methods to tackle problems involving large deformation, typically for foundations, but also for other applications. He's led the development of practical constitutive models for geomaterials that exhibit initial structure and hence high peak strengths, but which subsequently soften during accumulation of strains. No doubt we shall hear more of these applications tonight, and also of some of the pitfalls of the range of constitutive models that are available these days in commercial packages. John's work is characterized by scientific rigor and also insight into the most important aspects of a given application. One of the most highly cited of his 200 or so journal papers is his 1986 analytical solution for cavity expansion in cohesive frictional soils, including the limit pressures reached after large expansion. This and other studies for undrained conditions have direct application in estimating the end-bearing pressures for displacement piles and other deeply penetrating objects. There's much more that could be said of John's scientific contributions, but his career has been much broader than that, and I'd like to mention some aspects of his leadership in both academia and industry. He had key roles in 2 centres of excellence funded by the Australian Research Council, leading the Sydney node and research theme on foundations in the Centre for Offshore Foundation Systems based at the University of Western Australia, and he was on the management board of the Centre for Geotechnical Science and Engineering based at the University of Newcastle and directed by Professor Scott Sloan. On the management side for the ARC, he chaired a number of panels, including the main expert advisory committee in engineering, and also for the selection of research networks, and then in 2005 for the Federation Fellowships. Within industry, John has been extremely active as a consultant and board member of various enterprises. In 1995, he joined the fledgling specialist consultancy Advanced Geomechanics as a director, a position he retained until the company was bought by the Netherlands-based Fugro in 2013. He was also closely involved with the early concepts of the development of PROD, an underwater robotic drilling, sampling, and in situ testing tool that started out as a spin-off company from the University of Sydney. John represented the university's interests on the board of directors in the early years of Benthic Geotech, which still operates PROD today worldwide. He's also been a director of UON Singapore, the Singapore-based entity of the University of Newcastle and of the Newcastle Port Authority. And he was elected Vice President of the Australia-New Zealand region for the IWSM-GE from 2005 to 2009, and was recently chair of the delayed 2020 International Conference of that society held in Sydney. Since retirement, which seems more nominal than actual, John's services have been much in demand on expert review panels, mainly for the Government of New South Wales, including high-profile cases such as the Opal Tower in Homebush and the Mascot Towers in Mascot. In 2019 to 2020, he was also served as a commissioner for the Paradise Dam Commission in Queensland. You can appreciate that it's been very difficult to do justice to John's illustrious and multifaceted career as a scientist and engineer. He has always seemed larger than life, both in his work and as a magnanimous friend and colleague. I know that we are about to be intrigued, educated, and entertained by the topic he has chosen tonight. So on behalf of the British Geotechnical Association, I now invite Professor John Carter to deliver the 61st Rankine Lecture.
My Lord, ladies and gentlemen, good evening. Thank you, Mark, for your very generous introduction. I'm very pleased and I'm honoured to present this, the 61st Rankine Lecture, and I'm particularly grateful to the British Geotechnical Association for selecting me to receive this singular honour. I also want to thank everybody in this room for turning up. I know it's not been an easy many of you may have not found it easy to get here tonight, so I'm both grateful and gratified that you have come to listen, so thank you. In choosing a topic for this lecture, which took some time, but I eventually decided to return to an area of theoretical geomechanics to which I had been attracted since the beginning of my academic career, and it's an area that I've returned to on several occasions since then. I'm talking about modelling the response of geomaterials to various forms of perturbation, specifically stress strain or constitutive modelling. And today what I want to do is address the mechanical response of various types of soils and review the progress that we've made on this topic over more than half a century. But before I begin talking about technical matters, I believe some acknowledgements are in order. And if I may, I'd like to point out that I've had the pleasure of many collaborations during my career, but in particular I'd like to acknowledge people who were very influential during my formative years in geotechnical research. And they include Harry Poulos, who was and is an inspirational teacher, and he first introduced me to the joys of soil mechanics at the University of Sydney. And then Ted Davis, who was frankly a great engineer and a wise PhD supervisor. And incidentally, I am the fourth of Ted's former students to be invited to present this prestigious lecture, and the others were Harry Poulos, John Booker and Kerry Rowe. And I must acknowledge John Booker. As Mark said, I worked with him for many years in research at the University of Sydney, and he taught me many things, including some very useful mathematics. Bob Gibson, who generously and expertly supervised my time at King's College London in 1974, and of course Peter Roth. It was Peter who really opened my eyes to the wonders of constitutive modelling in the 3 wonderful years I spent at Cambridge University in the late 1970s. And I'm indebted to all of them and to others, and sadly, of these 5 giants of our discipline, only Harry is still with us. Of course, I must also acknowledge my wife Heather, who's here, and my family for their patience and forbearance while I went off and pursued my research dreams. Well, here's an outline of what I want to talk about tonight. I'll begin with some introductory remarks about modelling and talk about classifying soil models. I want to confine myself to conventional elastoplastic models and talk about their development. And I'll spend a little bit of time, I'll spend a little bit of time talking how to choose a model, a most appropriate model for a given problem, a little bit about how to evaluate whether they're effective or not. Also talk about the thorny issue of determining the values for the parameters of the model. And towards the end of the lecture, I'll talk about some complex boundary value problems and the role of the constitutive model in their solution. My major aims in this presentation are twofold. Firstly, I'd like to present my own interpretation of what's happened in this field of significance in this field over the last 50 years or so. And secondly, I hope to convince you, if convincing is indeed necessary, of the importance of understanding the capabilities and especially the limitations of the models we use in our advanced numerical analysis these days. Many of the models that I will mention are now available in commercial software. So I think it's incumbent on those using that software and even those directing its use to understand how such models behave. But let me begin by making a few introductory remarks about modelling in general and constitutive modelling in particular. And I think we'd all recognise that modelling is now an important aspect of geotechnical engineering. I would argue that the development and use of constitutive model involves both art and science, and I hope that will come through during this presentation. I believe it's important to understand that in any application we choose, the model we choose to adopt really is dependent on the questions that are being asked and on the particular predictions of the behaviour of the physical system that we're interested in, obviously. But we should always remember that models are merely imperfect idealisations of reality. Perhaps the best way, or a good way to illustrate what I mean, is to consider the problem of a ship at sea, and I'm indebted to Professor Calladine of Cambridge for this nautical example. If you're the navigator of that ship, you're probably only interested in where it is in space, where it is on the ocean, what its coordinates are. So your model of that ship may be just simply a point in space. But if you're the pilot or the captain of that ship and you have to bring it into port and bring it alongside a wharf, I think you'd need more than a conceptual model that involves just a point. You probably need to know where the bow of the ship is and the stern of the ship and the beam so that you don't cause any damage. And you can extend this analogy. If you're the hydrodynamics engineer designing the hull, your geometric or conceptual model at least would be probably more than what I've just described. We really need to think about what are we trying to do, what are the aims of the exercise, what questions are being asked when we decide on how complex the model should be. I first need to sound a warning though, a message that always needs to be kept in mind in my opinion, and it's probably most succinctly stated by the British statistician George Box when he wrote that all models are wrong, but some are useful. And essentially they're all wrong because they're only ever approximations, and no amount of elaboration will ever make them absolutely correct. And he also went on to state rather pointedly that we shouldn't over-elaborate when developing our models. And he also said you need to think about, well, what are the really important issues? Don't get sidetracked, in other words. Well, what are constitutive models for soil that I'm talking about? Simply they are mathematical relationships between stresses and strains. And as I'll address this issue in a little more detail as we go on, let me assure you at the outset that as much as possible I will be emphasising the physical concepts embodied in the constitutive relations, and I'll try very hard not to obscure that with complex mathematical detail. Well, this slide addresses the question of why develop models at all. In computational geomechanics, we generally seek mathematical solutions to what are known as boundary value problems or initial value problems. And very often in doing so, we would represent our soil body as a continuum. And it's useful to remind ourselves that these boundary value problems are usually formulated as a set of differential equations which might be subjected to particular conditions. These equations would set out in mathematical detail the three conditions of equilibrium, compatibility, and the constitutive relationships that have to be obeyed. And it's the last that I'll be focusing on in this lecture. Now, over the last 5 or 6 decades, there's been an explosion in the number of journals and journal and conference papers devoted to this topic. There are also textbooks, excellent textbooks written on the subject. In fact, there are so many publications that it's exceedingly difficult, I find, to keep on top of the subject and be alert to all the new ideas. There's a website devoted to the topic as well, which is rather useful. In fact, there have been so many developments that it's impossible to cover them all adequately in one lecture, and so I will necessarily have to be selective, and I'll consider only a very small subset of the models that have been published to date. And in the main, I'll concentrate on models developed either for single-phase soils or saturated soils to describe their behaviour under statically applied monotonic loading. I will briefly mention models for cyclic loading as well. Well, it's useful to consider the various ways we might classify constitutive models for soils, and physical scale can be quite useful. We can model at various scales all the way from the quantum up to the continuum, and if you're doing molecular dynamics, of course, you'd be working at the atomic scale. If you're trying to resolve microstructure of a material, you'd be at the mesoscale. But if we're analysing engineering structures, what we mostly do, we're normally working at the continuum scale, and this lecture will focus on models at the scale required for continuum analysis. And you can develop those models in at least 2 ways. You could upscale from the lower scale to the higher by homogenising in some way, or you could simply dream up relationships between the stresses and the strains. And I would call that a phenomenological approach, and that's the one that I'll be talking about in this lecture. Now, there are several factors that complicate, a number of factors anyway, that complicate the stress-strain behaviour of soils, both natural and reconstituted. They complicate the mathematical treatment because of the non-linearities they introduce, and I've listed some of the more important ones here. And first, we know that most soils either harden or they soften during loading, and sometimes they do both. We also know that changes in volume often accompany the shearing of the soil. The behaviour of natural soils is often different from that same soil that's been reconstituted in the laboratory. And in particular, they may possess a structure and a fabric, and they may exhibit anisotropy. Some soils are susceptible to the rate, the response they provide. It depends on the rate at which you load them, further complicating the issue. The loading may not be monotonic in reality. It may be cyclic, or repeated loading may be. And then we have the age-old problem of how do we determine the parameters. That can be very problematic. Well, let me now explore some of the advanced constitutive models for soil continua. And in doing so, it's worth keeping in mind the fact that this is an area of research that continues to expand, and new models seem to appear quite regularly. Given the time constraints, I'll focus solely on what I've called conventional elastoplastic constitutive models. And one of the earliest suggestions that soil could be idealised as a work-hardening elastoplastic material was presented in the famous paper by Drucker, Gibson and Henkel in 1957. It was in this paper, the authors didn't flesh out the detail of how this could be done, but nevertheless they pointed the way forward. And at about the same time, as we know, research at Cambridge was putting some flesh on these bones that was suggested by Drucker and others. And it was followed about a decade later by the first textbook describing critical state soil models. Well, I'd like to spend a little time reminding ourselves about the essential components of such models. And one of the fundamental assumptions is that the strain consists of two parts: an elastic recoverable component and a plastic irrecoverable component, and they're usually assumed to be additive. So, if I may, let us delve further, investigating, first of all, the recoverable or the elastic part. Now, ideally, what's required for elastic behaviour is a model that predicts a conservative response. And by conservative, I mean if a soil element is exposed to a closed loop in stress space, then there should be no change in the configuration of the soil element. There should be no net strain. And this corresponds obviously to no generation or no absorption of energy. Well, perhaps surprisingly, not all the so-called models based on the theory of elasticity that we're familiar with, and some of which we use routinely, not all of them can boast this claim. And within the theory of elasticity, there are at least three subclasses of model. They're the hypoelastic, the elastic, and the hyperelastic model. They're distinguishing features, and some and some examples of them are in this table, which I don't intend to go through in great detail. Probably the most familiar is Hooke's law. The least restrictive form of the models are the so-called hypoelastic variety, and a classic example is the nonlinear elastic model introduced by Duncan and Chang way back in 1974. And similarly, if we want to focus now on the elastoplastic constitutive models, there's a similar hierarchy or division into classes. Many of you will be familiar with the existence of modified Kamm-Clay, and it's probably the most famous. It's what I'm referring to here as a conventional elastoplastic model. But in recent years, there's been a growing body of research focused on the so-called hypoplastic and hyperplastic models for soils. And one of the main distinguishing features of the hypoplastic models is, unlike the classical elastoplastic models, there's no need to split the strain into the elastic and plastic components. The major advantage of the hyperplastic models, and there are some experts in this field in the audience, I know, the main advantage is the fact that those models automatically satisfy the second law of thermodynamics, and so in that sense they are arguably the most theoretically rigorous form of elastoplastic model. Now, the table I'm showing here would be reasonably familiar, I would hope. It describes the essential components of conventional elastoplastic models. And, of course, various laws could be adopted to describe the elastic component of straining, but Hooke's law is probably the most famous. But when it comes to defining the plastic component of that strain, we need four quantities or functions to be defined, and they are, first of all, a yield criterion, which is usually imagined as some surface in stress space which identifies the combinations of stress that cause plastic straining. The second plasticity component is something that determines the relative magnitudes of the plastic strain components. The third component or function determines the actual magnitudes of those plastic strains. And of course, at the end of the day, we need a failure criterion that places a limit on the stresses that can actually be reached. And the critical state line is a particularly good example of such a limit. Well, if I may, I'd like now to present my own interpretation of some of the history of model development with some of the more significant developments. Here it is in a single slide. It's a very busy slide, so I will attempt to unpick it and talk about the various stages in a little more detail. Well, early model developments were based on experimental data from so-called single-element laboratory tests on reconstituted soils, and we still rely on the results of such tests today for model development. But in the early days, the models were simple extensions of theories developed for metals. But unlike metals, of course, we know soils are particulate materials, and so major departures from those theories were required. Kamm-Clay and modified Kamm-Clay are notable examples of those earlier theories that took into account this particulate nature and specifically allowed coupling between the volumetric and the shear behaviour. But it's important to reiterate, they were developed based on experimental data for reconstituted soil, so in my mind it would be unreasonable to expect them to describe adequately the behaviour of and many complicated aspects of the mechanical behaviour observed for natural soils in situ. An obvious example of these early models is the more Coulomb elastoplastic model, which would predict the behaviour in triaxial compression that you see illustrated schematically in this slide. That is a bilinear stress-strain response and unlimited dilation during plastic shearing. Now, obviously, this type of response has clear limitations when applied to real soils. In particular, real soils just don't go on dilating forever. Cam clay and modified cam clay that I mentioned, they were very significant developments. For probably the first time, they provided the details of a complete strain hardening model for soil. And I won't spend any time going into the detail because the salient features should be fairly well known. But for the first time, we had a model that predicted in detail the effects of consolidation, for example, on shear strength. And I think that was a major achievement. Well, improvements to those early models were aimed at simply at providing more accurate descriptions of the mechanical response of real soils. And some of these developments included the suggestion of, well, maybe we could use more than one yield surface, allowing the possibility of different surfaces controlling the volumetric and the shear strain hardening. And there are many examples of this type of model now available. And examples include the sort of various hardening models that you can find encoded in commercial software packages. It's possible that some or all yield surfaces may be engaged simultaneously so that hardening or softening could occur, theoretically, it could occur simultaneously. And then moving on, there was recognition that soils really exhibit, many soils anyway, exhibit anisotropic response to loading or unloading. That is where the response may be directionally dependent, either intrinsically because of the nature of the soil or induced by the stresses that are being placed on the soil. And that realisation fostered the development of a whole subclass of elastoplastic models. There are numerous examples of this type of model in the literature. Just as an aside, the mathematical formulation of models to describe anisotropy requires the use of all 6 stress components or some meaningful combination of them. And this contrasts with models that describe isotropic behaviour that really only need 3 stress invariants to completely describe the behaviour. Now, models of this type generally involve a plastic potential surface that is often different from the yield surface. In other words, they employ what's known as a non-associated plastic flow rule. And furthermore, the yield surface may be a kinematic yield surface. That is, not only can it expand in stress space as the stress level increases and the soil deforms plastically, but it may also rotate, allowing the directional dependence of the behaviour to be captured. And here's an example of a comparison of some of the predictions of the behaviour of Toyura sand, which exhibits anisotropy. And you can see that the comparison of the model predictions with the results from hollow cylinder tests shows quite promising agreement. Our further model complexity and capability was added over time due to the desire to model the hysteretic response that we see when we apply stress reversals or so-called cyclic loading. In the main, that's been achieved in one of 2 ways, either with multiple nested yield surfaces or with a single yield surface that can either change its size or its shape as the loading direction changes. And I'll attempt to just briefly illustrate both of these methods. But first I need to mention the concept of a bounding surface. It's an important concept that was introduced by De Falius and others. And in some models of this type, the yield surface may expand inside the bounding surface while it obeys some mapping rule as shown in this sequence of slides. And the following animation shows an example of the bubble model approach to describe cyclic loading, which employs a bounding surface. So for a soil that's initially K0 consolidated and then unloaded and reloaded, the progression may look like this cartoon that you're looking at now. And it normally results in the prediction of a hysteretic response. I'll now briefly describe the alternative approach involving changing the shape of the yield surface during the loading. The particular example I want to show you adopts a useful generalisation of the modified cam clay yield surface, which was elliptical in this stress space. And the modification was originally suggested by McDowell and Howe, and they introduced an additional yield surface parameter, lowercase m, in this figure. And what the figure is showing you is the variations of the shape of the yield surface corresponding to different values of the parameter m. And the case where m equals 2 corresponds to modified cam clay. The more general form of the yield function is as shown on the lower right there, and when m is greater than 2, it causes the yield surface to slant to the right, and when m is less than 2, you get the opposite effect. So how do you use this in a cyclic loading problem? Well, if we now examine what happens if we allow that yield surface to change its shape during the cycling, we'll start out with a soil that's initially isotropically consolidated. The first half cycle of shearing causes the yield surface to expand, and of course that expansion, it's an undrained event, so it causes no volume change, provided the plastic and elastic strains exactly balance each other. Now, during the unloading, undrained unloading, the soil, in this case, in this model, would behave elastically, and it's isotropic, so the stress path must move vertically downwards. The yield surface size in this particular model needs to be maintained as constant to uphold the condition of zero volume change, but it may change its shape. And this can be achieved if you somehow allow that parameter m, which governs the yield surface shape, to be some function of the cyclic loading, the number of cycles, for example. So that by the time you go through up to 2.5 cycles of loading, you would have changed the shape in various ways. And the trick in applying this to the cyclic loading prediction of cyclic loading behaviour is to define how does that parameter m change as the cycling changes. One possibility is indicated in this diagram. There could be many other choices, and of course it has to be recognised this is a purely phenomenological approach to the problem, but I would contend that it does have some utility. And an example of the consequences of adopting it are shown here. The top half of the figure shows how the yield surface shape may change during cycling, and the lower figure plots the corresponding changes in the predicted changes in the excess pore water pressure during the undrained loading. And here's a plot showing a match-up between simulations with that type of model and some experimental data obtained in undrained cyclic triaxial tests on a high plasticity clay soil. Well, this is a bit of an aside, but perhaps it's curious, I think, that there's already been a great deal of work investigating constitutive models that can be used to predict soil behaviour under rapidly applied cyclic loading. I'm talking about problems that involve a dynamic loading component as well as simple reversal of the load, the sort of loading you'd experience during an earthquake. And I won't be covering this aspect in this lecture, but I'd refer you to an excellent summary that was a state-of-the-art paper in the most recent ISSMGE conference held in Sydney. And in that paper, the author Ross Boulanger made great use of and great reference to a very detailed set of liquefaction studies reported in the proceedings that I've just brought up on the screen. Well, moving on, another feature of real soil behaviour that has been incorporated in our advanced soil models is the effect of soil structure, and in particular any effects of destructuring, or some may call it destructuration, that occurs as the soil is further loaded or perturbed. And these models should generally provide predictions of real soil behaviour that will eventually approach the behaviour that you observe for a reconstituted soil as the structure is progressively removed by the continued loading. So they require specification of how destructuring will occur with loading. But before moving on to that, let me just try and illustrate some of the features we're trying to capture when we are modelling structured soils. Here are some data, some consolidation data. It's a plot of specific volume against the consolidation pressure. And what you can observe is the slightly stiffer response of the undisturbed structured soil and perhaps just the suggestion that it takes a higher pressure to mark the onset of plastic yielding of that structured soil compared to the one that the structure's been removed. And if one conducts shear tests on a structured material and compare it with the reconstituted, same soil that's just been reconstituted, you might get a comparison like you see here and a suggestion that the structured material might have a higher peak strength. So they're the sort of features that we need to capture in our models of structured materials and the progressive destructuring that will occur once we continue on with the loading. So some of the distinguishing features of successful models for structured soil are, firstly, the structured material should have a larger yield surface and larger voids ratio at the same value of mean effective stress. And you need a means of describing any destructuring or destructuration that will take place with increasing stress level. Well, several approaches have been suggested for modelling this class of material, and in 1993, Antonio Jens and Roberto Nova suggested one such approach. And they assumed that the ratio of the sizes of the yield surface, the one for the structured soil compared to the one for the reconstituted soil, that ratio could be described as some function of plastic straining and perhaps, more specifically, some combination of the plastic volumetric and plastic shear strain components. And it seemed a sensible way forward. An alternative and admittedly a phenomenological approach describes how the additional voids ratio that arises from the presence of that structure, how that would decrease with increasing mean stress level. And the essential components of that model are shown in this slide. The isotropic consolidation of a reconstituted soil will normally plot approximately as a straight line, shown here in red. And by contrast, the same soil with some structure would have an isotropic consolidation path that I've shown here as green. And apologies to those who may be colourblind for my thoughtlessness. Well, you notice that at any pressure, the two curves are separated by an additional voids ratio I've called delta E. There are the two portions of the green curve, there's a sort of division at a pressure I've shown on here indicated as PC naught. So at any consolidation pressure less than PC naught, it's assumed that the behaviour is elastic and therefore recoverable, but beyond PC naught, plastic straining takes place, and this is described as virgin yielding. And we discovered that a simple exponential function could be fitted to that data for a whole host of soils that we looked at. So one can describe the descending, the plastic portion of that curve for the structured soil by defining how the voids ratio that's sustained by structure gradually reduces. Well, I'd like to show you some examples of how well, or perhaps how badly, depending on your point of view, the structured camp clay model performs in simulations of real laboratory data. I'll only show a couple, but I think they're representative. Here's some isotropic compression data for 4 different structured soils. We've got a cemented calcarenite, a marl, and 2 different clays. The experimental data is shown as the symbols, and the solid black curves are the simulations, and a reasonable match can be obtained. If we look at shear loading, on the other hand, we've got some drain triaxial compression tests on a clay shale at different confining pressures. And again, the symbols are the experimental data, coloured lines are the simulations, and again, reasonable, not perfect, but reasonable agreement, I would suggest. Well, moving on again, one of the most, in my opinion anyway, one of the most difficult features to include in soil constitutive models, and probably the least developed area of research, not that, I mean, people are working on it, but I think trying to work out how to effectively and adequately include the rate of loading and the effects of the rate of loading into a constitutive model is an area that I think needs more work. And the way this is done at the moment is either you introduce some form of creep law which into the constitutive model, which requires, then invokes the theory of elasto-viscoplasticity, or you can use what's known as the isotash approach, in which case the behaviour is assumed to depend on the rate of straining in some way, and I'll try and illustrate that. So, as I said, one approach includes the assumption that the size of the yield surface is not only a function of stress and perhaps plastic straining, but also a function of the applied strain rate, so that with faster loading, faster strain rates would correspond to larger yield surfaces and consequently a stronger soil. So you can see the sort of complexity that's been added. And this slide shows a comparison of some experimental data represented by the symbols and simulations that include rate effects that I talked about. The obvious transition in the curves correspond to changes in the value of the imposed strain rate. But within each section, the strain rate remained constant. And you can see it's possible to get a reasonable match. But as I said, I think there's still scope for further work. An alternative approach utilises, as I mentioned, the theory of elasto-viscoplasticity. And this slide shows a comparison of some predictions of a rate-dependent viscoplastic model with field observations of the centreline settlement of an embankment in Finland that was constructed on a sulphide rich, moderately sensitive, highly anisotropic silty clay deposit. And it's obvious that the model, known as EVP S-Clay 1, can provide accurate simulation of the real behaviour of an embankment that is on a creeping soil. If I may, I'd now like to mention the quest to obtain a unified soil models. I mean, models that can cover all types of soil regardless of particle size, where the only difference, say, between a sand and a clay might be the choice of the values for the model input parameters. And there are several examples of these models in the literature. They include a model known as CHASM, clay and sand model, I think it stands for. But there are also various bounding surface models that I mentioned previously. If I may, I'd like to just talk about one of them. It's the model CHASM, developed originally by Hai-Sui Yu and later extended by him and his colleagues. And a key feature of this model is the incorporation of what is known as the state parameter, which I should now describe for those unfamiliar with it. In my opinion, it's one of the very significant developments in constitutive modelling over the past 50 years, and it involved the introduction of this concept of a state parameter by Bean and Jeffries and recognition of its significance. It has a simple definition. It's the difference between the current voids ratio and the voids ratio on the critical state line at the same mean effective stress. In other words, just simply the vertical distance of the current stress point to the critical state line. It turns out that this parameter is very significant in determining how granular soils will behave when loaded. For initially dense sands that must dilate to reach their critical state, the parameter psi, or the state parameter, takes negative values, and if the sand is initially very loose and must compress to get to critical state, then the state parameter takes positive values. And this slide shows a comparison of some of the model simulations of CHASM and experimental data from true triaxial tests on Toyura sand. And the comparison indicates that this model can provide very reasonable, indeed impressive simulations for quite a range of quite complex stress paths. Well, before moving on, I should remark that there are numerous constitutive models now that incorporate this state parameter psi, and I've listed some of them on the slide. Well, an important question, I think, that always should be on an analyst's mind when they're tackling a problem in computational geomechanics is, well, which model should I choose? Of course, not all published models have been implemented in commercial software, so the choice may be simple. Not all may be readily available, unless, of course, one wishes to encode them in bespoke software or in commercial packages that allow the user to define their own model and provide the software that does the calculations. But in answering a question like this, I think some heed should be given to the words of Deng Xiaoping. We shouldn't overcomplicate matters, in my view anyway, and parsimony is generally a good thing in this regard. Well, that said, I think we should also appreciate that there may be more than one model that will fit the bill. More formally, we can consider a typical list of the factors that may be taken into account when selecting a constitutive model. They should obviously include the type or types of soil you've got, the loading that you're anticipating, and any particularly important or peculiar aspects of the problem that you're examining. And we'll see later in an example I will present how the choice of the wrong model can have quite catastrophic consequences. So in making the choice of model, it's always wise to consider the likely stress paths that elements of the soil in your boundary value problem or your application, what sort of stress paths will elements of soil be undergoing or experiencing. And I'm really indebted to Professor Carstoonen for this cartoon that I think illustrates the point rather well. It shows typical stress paths that might be traversed by soil in different types of boundary value problem, different types of application. So one of the most important considerations should be what type of application do you have in mind, what problems are you trying to solve? And I'd like to look at this issue in a little more detail, and I confess this is another very busy slide, so if you will allow me to unpick some of it, I will do so. For example, if the problem at hand involves embankment construction, then the following model features are probably be important. The loading will mostly involve soil compression with perhaps some shearing and stress rotation under the edges of the embankment. The strain levels you might anticipate are likely to be relatively large, and you might also need to think carefully whether rate effects should be included, because often you're on very soft soils that creep. On the other hand, if the problem considered involves excavation or retention of soil, then unloading and decompression of that soil will be important, and normally would involve low to medium levels of straining. And in such cases, it's more likely that models that include stress-dependent stiffness will provide more accurate predictions than some simpler models. And so on for the other types of application. I won't go through them all here, but a form of this table will appear in the written version of this lecture. As I said earlier, another important issue is, well, what models are available in commercial software. I foolishly started preparing a list, or it turns out it was foolish, of what models were available in commercial software some years ago. But I eventually came to the conclusion this was a rather futile exercise, but simply because the scene was changing quite rapidly and any list would soon be out of date. But I did note that more Coulomb and modified CAM clay models appear to be ubiquitous in the commercial software. In this day and age, one can simply trawl the internet and look for software user manuals to see what models are available. Or as shown in this slide, you can make use of artificial intelligence tools that are becoming readily available to do that trawling for you. Who knows, one day they may be able to produce a Rankine lecture for you. But anyway, let me now address the problem of how do we or how should we evaluate the accuracy and the effectiveness of a soil constitutive model. Before addressing that particular question directly, it's worthwhile to consider more generally or more broadly what influences the accuracy and quality of the numerical predictions, the predictions of our numerical models. And a neat summary of the major influences was provided in a recent paper by Boulanger, and the major factors he listed I've also repeated here. And apart from the obvious factors such as how well you've characterised the soils at the site and characterised the site itself, and how clever your numerical tool is, the choice of the constitutive model and how well that model has been calibrated are also very important. A thorough evaluation of a numerical model prediction may involve several stages, and the first usually involves comparing predictions of your chosen constitutive model against the results of single element laboratory tests conducted on soil samples in the laboratory, and that's a process that I would, and many would call calibration. A second stage in working out how good your numerical model is, you might want to compare solutions of your numerical model with known solutions for boundary problems for which there are either exact or even approximate solutions. And a particular example is the cavity expansion problem that I'll talk about in just a moment. The last step is the relevance of the numerical model. How do you ascertain that? Well, there's really no other way than comparing the predictions of your overall model with the results of experimental tests, either conducted in the laboratory at 1G or in a centrifuge, or alternatively by comparing its predictions with field measurements. And probably that's the ideal way to do it. I'd like to spend just a little time exploring the solutions to some cavity expansion problems because I think they can be very revealing. And the problem has numerous applications in geotechnics and it has some rather obvious advantages and limitations, as I've indicated in this slide. One of the major limitations is the fact that it involves no rotation of the principal stresses. So a schematic representation of the problem in an elastoplastic soil continuum is shown here. The cavity could be cylindrical or it could be spherical. It's normally assumed the soil is under an initial isotropic effective stress P0, and as the internal cavity pressure is increased, the soil in the cavity begins to expand, and the soil in the immediate vicinity of the cavity wall will eventually yield plastically, and the plastic zone will grow as the internal pressure continues to increase, and eventually you'll get to a limiting pressure. So as an example, I'd like to examine cavity expansion in sand, assuming fully drained conditions. And the literature contains numerous solutions to this problem. And in this lecture, I just want to consider two of them. One involves good old Moore Coulomb, but a version of Moore Coulomb that has a restricted amount of dilation. The dilation doesn't go on forever. And the other I want to consider is a more sophisticated sand model known as Norsand. Here's a schematic representation of the behaviour in triaxial compression of the ideal Moore Coulomb model with limited dilation. And a really important quantity here is the plastic volumetric strain at which the dilation ceases. So it's a fairly simple model. And here are some results if you apply that model in a cylindrical cavity expansion problem. And you can see that, well, what we're seeing here is the limit pressure, normalised limit pressure on the vertical axis, and that quantity, that maximum plastic volumetric strain that can be developed is on the horizontal axis. And you can see that the limit pressure is dependent on that maximum amount of dilation you assume. It's also dependent on the rate of dilation, as shown by the different dilation angles there. The endpoints on these curves are of some interest. The blue circle corresponds to the case where you allow no dilation, so it's a material that doesn't dilate at all, and it's got the lowest predicted cavity pressure, as you might expect. The brown squares are rather interesting. They correspond to the case where the limit pressure at the cavity boundary is reached at exactly the same instant that the maximum plastic volumetric strain is reached at that boundary. If there's no limit on the dilation, you'd get a limit pressure predicted by that arrow I just introduced into the figure. And finally, we can see that if even a limited amount of dilation does have a very significant effect on the predicted limit pressure. For example, I've just brought up, if you allow a modest amount of plastic straining of 10% volumetric strain, for the case I've shown, the limit pressure is increased by 65% above the limit pressure in a soil that would not dilate. And this can be compared with 93% increase in a material which is allowed to go on dilating as long as it wishes. So it's a case of a little bit of dilation going a very long way in a highly constrained problem like this one. Clearly, the constitutive model does not require great complexity in order to provide some meaningful clues about the behaviour of this ideal material, and especially if you're interested in limiting conditions. Now I'd like to turn the focus on a spherical cavity expansion in ideal North sand soil model. And I've chosen the parameters here for the North sand model to correspond to Toyura sand. And in this case, the limit pressures are predicted to be very dependent on the initial density of the soil as reflected by the initial value of the state parameter that's plotted on the horizontal axis. And we could think of these limit pressures in this spherical cavity problem as indicative at least of the ultimate tip resistance of a driven pile in sand. And if so, this model is telling us that the tip resistance is very dependent on the initial conditions of the sand. For example, if the soil is initially very loose, the sand is very loose, then that tip resistance might be, in this example, would be on the order of 500 kilopascals. But on the other hand, if it's very dense, you could get limit pressures, predicted limit pressures at least, to be 10 times that value. So clearly the power of a more sophisticated model like this is being able to capture the important influence of initial density and the subsequent volume changes that have got to occur or will occur during shearing, and what effect they have on the behaviour in the boundary value problem. It brings me now to the question of, well, how do we determine values of the input parameters for a given soil model? Often a very vexed question in my estimation. Now, as previously mentioned, calibration may involve a combination of processes, including fitting the model to the results of a variety of data sources, including, as I've pointed out, single element tests, all the way up to multi-element field tests. And it will very often involve, in practice, it'll involve a lot of judgment and some curve fitting, especially if the parameters being assessed do not have obvious physical meaning, and quite often they don't. Well, I don't have time in this lecture to talk about specific models and how one would go about determining the values for each and every one of their parameters. But what I would like to do is make an appeal for modellers to provide clear guidelines for how they suggest these parameters should be determined. And if you will allow me, I'd like to point out a very recent example of what I think is good practice in this regard. And it appeared in a very recent paper. And the authors provided a flowchart that guides you through the process for determining values of their model's parameters, and it's most instructive. Not only does it advise what type of test should be used to identify certain parameters, but it also provides useful advice of when, and importantly, when not to adopt their model. And in my opinion, it would be very useful if others would follow this type of example. That said, I should acknowledge that such advice has been provided and presented in the past by other model developers, not necessarily in the form of a flowchart. It's clear guidance on how to select the parameter values is what I would really like to see, and that's not always been the case. And by way of confession, I would count myself amongst the guilty. So that brings me to the part of the presentation in which I'd like to demonstrate some of the things that one can do with the models we've developed up to date. I must stress again at the outset that successful application of these models does require some compromise and some approximation, and one does not always have to hand all the information, the hard facts and the data required to give you confidence that the correct model and the value of its input parameters are suitable for the problem at hand. And good old engineering judgment is usually required. And in this type of task, I personally believe in potency above purity. Well, selecting a model with the appropriate details is crucial, an obvious statement. It may be even a trite statement, but nevertheless it's true and shouldn't be forgotten. And I want to illustrate this point by considering several example problems. Some I will discuss in detail, and those I've identified here in the lower part of the table in red text, and others I'll simply refer to without detail in the interest of time. And incidentally, the list here is by no means exhaustive. It's merely meant to be representative. Some of the lessons to be gained from studying cases like these are well known in the research community, or at least they should be, in my view. But I do think they bear repeating here in the hope that they may assist others to make some sensible choices when considering which model to adopt and which features of the model are really important. And I've also included an example at the end of what can go wrong if an inappropriate model is selected. Well, firstly, to illustrate the effects of let's say, problem scale, I'd like to consider the relatively simple case of a rigid circular footing resting on a layer of uniform sand. And for this problem, we know that the bearing capacity factor, N gamma, depends on the shear strength of the sand layer, which in turn may depend on a variety of factors, such as the ones I've listed here. And the initial density of that sand will normally be a very important influence, and it's what I want to examine. But accurate numerical predictions of the bearing capacity factor N gamma require the use of quite advanced constitutive models. Some I've listed here. And in order to be specific, I'll initially consider the use of Knorr sand, which we've seen before in the lecture. And here's a sequence of predictions of the load settlement response of circular footings of varying diameter on a layer of initially dense sand. And I've chosen the model parameters to be representative of Toyura sand, which has been well studied and well documented. And you note the very marked effect of footing size. As the diameter increases, the predicted peak bearing capacity factor reduces, and this is, I believe it's consistent with our practical experience. And you note that the post-peak softening seems to reduce for the larger footings. And if a 100-metre diameter circular footing worries you, just think offshore gravity platforms. Now here's a plot of the predicted peak bearing capacity factor versus footing size, and they are all for these hypothetical samples of Toyura sand that are very dense with an initial voids ratio of 0.65. It turns out that the peak values are sensitive to the location, where you assume the critical state line is in voids ratio mean effective space, and that position is represented here by the value of the parameter I've denoted with a Greek letter, capital gamma. Well, for initially dense samples, the larger the value of gamma, the further from the critical state line is the initial condition of the soil, so getting to failure will generally require greater shear loading. And just in case you may think these theoretical results are perhaps a tad fanciful, what I've just put up are the results for maximum bearing capacity factors observed in a series of centrifuge tests on Toyura sand, and the graph appears to show reasonable agreement. But in this context, I want to reiterate, all models are wrong, but some may be useful. Knorr sand, it turns out Knorr sand is not the only model capable of predicting scale effects in a bearing capacity problem, and similar predictions were made by Yamamoto at the University of Western Australia for footings on two different types of material, and he used the MIT S1 model developed originally by Pestana and Whittle. And one of the sands was the dense Toyura sand that I've considered previously, a silica sand, and the other was a loose calcareous sand. And the bearing factors as a function of size are shown in these graphs. And again, to provide further confidence in the use of such models, here again are the results of centrifuge tests carried out using circular footings. The degree of the alignment between the experimental data and the predictions, especially the trends, I think, is quite satisfying. Well, now I'd like to move on and present an example of a boundary value problem that involves large deformations, a type of problem that, as you heard from Mark, is near to my heart. My aim in presenting it is to demonstrate that the level of sophistication of the chosen soil constitutive model should match the requirements of your analysis, and I want to demonstrate the effect of allowing for various features that might present themselves as very large straining occurs. And in particular, I want to consider the significance of destructuring, rate effects and softening. And I'll do so by considering the problem of a pipeline laid on a seabed. Now, the various stages in the life cycle of a seabed pipeline are illustrated here, and although we could model all stages, I want to concentrate only on the first stage, in which the pipeline is laid on the seafloor, usually from a ship. And it usually occurs rapidly compared to drainage times in the soils on the seafloor, which are often fine-grained, and so it's often reasonable to model this as an undrained event. But if significant penetration of the seafloor occurs under the submerged weight of the pipe, then large straining of the seafloor soil will occur. So accordingly, for more realistic analyses, you might want to include the development of a residual strength. Well, let's first consider the penetration, and what I'm showing here is a variety of model predictions and a comparison of those predictions with the results of a physical experiment conducted in a geotechnical centrifuge. And we've got a plot of the normalised penetration versus the normalised force required to cause that penetration. I need to stress that all the models used in these calculations were first calibrated, at least to the extent that they could reasonably reproduce the undrained strength profile that had been measured by a T-bar in the centrifuge test, which of course showed a linear increase of strength with depth. Now, there's considerable difference in these predictions, but I'd suggest one could at least tentatively conclude that in this case, capturing destructuring and rate effects, for example, with the viscoplastic version of the Sarni clay model, that may be more significant than including anisotropy in your model. Well, a different but very similar pipe penetration problem was studied in detail, and we used a two-surface yield model, which had the additional capability of capturing softening of the soil as straining increased from critical state to the residual condition. And it was achieved fairly simplistically by using a two-surface model, as you see here, but one which allowed the friction angle to eventually reduce with straining. I won't go into the details, I'll simply move to the results. For this particular problem, we used the particle finite element method to simulate the penetration. It's well suited to large deformation problems of this type. And what you're seeing here are some predicted contours of accumulated plastic strain during the pipe installation and at different embedment depths. As I said, this particular set of results includes softening. And you can see that the localisation of the plastic deformation has occurred and narrow shear bands have been developed. If you were to use exactly the same model but left out the softening, you didn't allow the model to soften but everything else was the same, you'd have a set of pictures such as I've just put on the screen. Quite a different pattern of deformation predicted by simply ignoring the possibility of having some softening. And for comparison purposes, here's good old modified cam clay predicting the same sort of thing. That picture not so different from the one immediately on its left. Well, this slide shows a comparison of the normalised force that's required to penetrate the pipe for different cases, and modified cam clay is the blue dashed line to the right. The soil with the highest and largest degree of softening is the black curve to the left, and the others include different amounts of softening, and one includes, I think, some rate dependence. But clearly in this case, modified cam clay predicts more force is required to produce a given penetration compared to the other cases. But probably the most important aspect of this figure is the fact that you can see progressive failure. It's apparent to varying degrees for those cases that include a bit of softening. And what you can see is the soil resistance experiences a sudden decrease, a local decrease in resistance, after which another curvilinear localised failure zone begins to develop from the pipe invert to the soil surface. Well, moving on, in this context of considering boundary value problems, I'd like to mention a fairly recent prediction exercise that was associated with the Ballina test embankment in the state of New South Wales in Australia, because I think it contains some important lessons for the users of numerical methods and constitutive models. Well, in this exercise, people from all over the world were invited to predict various aspects of the behaviour of this heavily instrumented test embankment that was constructed on soft estuarine deposits. And the predictors were all provided with, well, it was a vast amount of laboratory and in situ test data. And the reason for providing it was to allow them to calibrate their constitutive models prior to them making their predictions of the embankment response. And shown here are some predictions of the time settlement response of the embankment together with the field measurements of that settlement shown in red. And it's obvious the large amount of scatter that has occurred in these predictions. And to many in this room, that may not be a huge surprise. And here is a little detail on some of the types of approach and the various constitutive models that were employed in this exercise, and there's quite a range of them. So you may well ask, well, what are the lessons from this type of activity? We've got such a large range of predicted results. Well, first I should note that there was a variety of constitutive models adopted, but most included some allowance for rate dependency and destructuring and anisotropy that I've spoken about. But the different models provided quite different results depending on who was making the prediction, their chosen constitutive model, and importantly, how much attention they paid to the task of first calibrating that model. And even those who adopted the same model and were given the same set of geotechnical data, they came up with, in some cases, quite different predictions. I can just note simply that the models that allowed for some rate dependence generally provided the more accurate predictions. And most importantly, what this exercise taught us, yet again perhaps, was the importance of the calibration process when making predictions of this type. It really is essential. I'd like now to end this section of the lecture and by considering providing a salutary reminder, I hope, a reminder that the choice of the constitutive model can sometimes be crucial, and indeed the selection and use of the wrong model can be catastrophic. What is shown in this image, and so it may be quite familiar to many of you, it's a case study that has been well documented. It's the collapse of the Nickel Highway in Singapore that occurred on the 20th of April 2004. And the collapse occurred during excavations associated with a section of the underground railway system, or the MRT, the Mass Rapid Transport System in Singapore. Now, the collapse was the subject of a formal inquiry, and the committee charged with undertaking that inquiry reported that there was, and I quote from the report, and abuse of the back analysis, end quote. I should note that most of the soil at the site was a soft marine clay. And in effect, the wrong constitutive model was adopted in numerical analyses of the wall, conducted both at the design stage and in the back analyses conducted during construction. And this was identified as a key factor contributing to the collapse. There were other factors, it wasn't alone, other factors contributed, but certainly choosing the wrong constitutive model was an important contributing factor. And I'd now like to attempt to explain briefly and in simple terms the error in that choice of the constitutive model. Now, this is a figure taken directly from the report of the inquiry, and it indicates some critical details of the constitutive modelling adopted and that which should have been adopted during the numerical analysis at the design and back analyses stages. Well, according to the official report, the design adopted an effective stress analysis using our old friend, the Moore-Coulomb stress-strain model. But in order to approximate undrained conditions, a value of Poisson's ratio close to 0.5 was selected. Now, as a consequence, the stress path to shear failure would have had to maintain a constant value of mean effective stress, so that the path for an element of soil to shear failure would have risen vertically on this graph, giving rise to a mobilised undrained shear strength that can be deduced from the intercept on the vertical axis in this plot. And this technique was denoted as method A. It significantly overestimated the undrained shear strength that could be mobilised in that soft marine clay. A more accurate approach should have been adopted, such as the one denoted here as method B. And the real stress path to shear failure would have been something like what is shown here by the green line that I've just displayed. Consequently, a Moore-Coulomb model based on a total stress approach with an undrained shear strength corresponding to the lower intercept on this vertical axis, together with a zero friction angle if you must use Moore-Coulomb, that would have been a more appropriate choice of a constitutive model. It would have resulted in a smaller, more realistic value of the undrained strength mobilised in the soft marine clay. Oops. And to quote the investigation report again, the problem inherent in method A is therefore a fundamental issue in constitutive modelling. And I would repeat, choosing the wrong model can sometimes have quite dramatic consequences. I'd like to wind up the presentation by recapping and stating just a few fairly obvious conclusions. Some of my comments may seem obvious, even banal if you will, but I do think it's important for us to recognise and celebrate what's been achieved over the years and what still limits the reliable use of numerical packages that employ our constitutive models. I focused here just on classical elastoplastic constitutive models. This is only a subset of what's out there and what could be used. But I would contend we have come a long way in 50 years, and you've got these advanced models now available in commercial packages. The trick is to use them correctly. I also should repeat that the perfect model has not been invented and probably never will be. And in this regard, I like to be comforted by the Japanese philosophy, which crudely stated is, there are three simple realities. Nothing lasts, nothing is finished, and nothing is perfect. I would also contend that you really need to know the details of your constitutive models if you want accurate predictions, certainly of deformations, and they will control the mode of deformation and ultimately the mode of failure, and that's particularly important in problems that are highly constrained. And may I end with a simple plea. I think it's incumbent on those who undertake numerical modelling and who frankly are brave enough to try and predict the future to simplify their models as much as possible. And in this regard, knowing what to ignore is really a key skill. That concludes my presentation. Thank you very much for your attention.
I now call on Professor Antonio Gens of the Universitat Politècnica de Catalunya to deliver a vote of thanks.
It's a privilege and also a personal pleasure to propose the vote of thanks for Professor John Carter, the 61st Rankine lecturer. We have just listened to a fascinating lecture on constitutive modeling in computational geomechanics. If you look back over the previous 60 Rankine lectures, you can verify that in spite of the importance and relevance of this topic, it has never been the main focus in any of them. Maybe this is due to the reputation of constitutive modeling as a dry, somewhat forbidding subject fit for specialists only. Well, Professor Carter has proved this view to be utterly wrong. He has made the material intelligible, interesting, and very relevant to most of us. Those who know John are aware that he likes to tackle problems head-on, and that's what he has done today. You have heard his motto, I believe in potency about purity, although I'm not sure what it's leading to. At the outset of the lecture, he has stated his two main aims. First, he would like to provide a brief history of the major developments in this field over the past 50 years or so. And secondly, he was hoping to convince us, the audience, of the importance of understanding the capabilities and limitations of the models that we use. In my view, he has succeeded brilliantly on both counts. Professor Carter is ideally placed to survey the advances of constitutive modeling over the last decades, because he has been there throughout. He was in Cambridge when the recently born critical state slow mechanics was starting to venture into the real world, and he is now still contributing exciting new developments. Some of them have been presented this evening. The scope of the subject is, of course, huge. He has very properly focused on the elastoplastic models that, by and large, are the ones we normally use in practice. And he has done it starting from first principles and gradually increasing complexity, while focusing on physical concepts rather than on mathematical detail. Having set the scene, Professor Carter has addressed the importance of understanding the models in all their aspects. He has informed us that the perfect model has not been invented and it will never be, so I'll be heavy is too complex for that. He has stressed the critical role of calibration and parameter determination, and he has provided wise advice for selecting the correct model, depending on the type of problem that we face and especially on the questions we ask. And he has also provided several examples of application as befits his lifetime experience in numerous engineering cases. Professor Carter has also ventured into the thorny issue of prediction. We, geotechnical engineers here, can admit that perhaps prediction is not our strong suit. Recall, for instance, the slide on the Ballina Tense embankment. As somebody unkindly said, the main function of geotechnical prediction is to make astrology look respectable. I'm paraphrasing, of course. The situation is not that hopeless, but there is a lot of room of improvement. The lecture this evening tells us that any such improvement will require the use of well-understood and well-calibrated constitutive models, able to reproduce the key features of soil behavior relevant to each particular case. In fact, we have been provided with useful guidelines in this regard. My Lord, ladies and gentlemen, we have been privileged to attend a memorable and stimulating lecture delivered in the enlightening and forceful manner that is John's trademark. I am convinced that it will soon become the first port of call whenever constitutive model issues come up. I remember during the investigation of the Nickel Highway collapse, mentioned in the lecture, an extremely experienced geotechnical engineer telling me plaintively, all my professional life I have known and applied the Moore-Coulomb failure criterion, but I was not aware of the Moore-Coulomb elastoplastic model. In the current state of practice, lack of knowledge of constitutive modeling may perhaps not be an option any longer. Therefore, we are extremely grateful to Professor John Carter for devoting much time and effort to prepare and deliver such a lucid, wide-ranging, and valuable lecture. On behalf of the British Geotechnical Association, I call on everybody here, and also those watching online, to give him our thanks by acclamation.
Well, thank you to everybody. As you know, this lecture is followed by the Rankine dinner. For those of you who have purchased tickets, the dinner is preceded by a pre-dinner drinks in the senior common room, and those will be available very shortly. For those of us, or for those of you not joining us for the dinner, there is at least one other option. The early career group of the BGA will be hosting an informal networking event at Imperial College's East Side Bar following the lecture. So the bar is located on the far side of Princess's Gardens, and signs should be in place to direct you. All lecture attendees are very welcome, and there will be a mix of non-alcoholic and alcoholic drinks available at that reception. As you can see on the slide, that event is sponsored by Tony G and Fugro, and they have sponsored the first drinks for early career colleagues on a first-come, first-served basis. So I think you can expect that this event will get off to a very prompt start. So at the dinner this evening, the next year's ranking lecturer will be announced. For those of you not attending the dinner, the name of the 2024 lecturer will be posted on the BGA website at midnight. So we're staying up tonight to find out that information. I'd like briefly to give some details of some upcoming BGA events. The 54th Cooling Prize competition for early career colleagues will be hosted as an in-person event at Cardiff University on the 27th of March. And that will be followed by the BGA's biennial conference, which this year is on the topic of georesilience. So the Georesilience 2023 conference, and that will be held at 28th and 29th of March, also at Cardiff University. And full details of those events and many others are on the BGA website. So without further ado, I'd like to say a big thank you to you all for attending this 61st Rankine lecture. I wish you an enjoyable evening. Thank you and good night.
Eso